I will continue to share more details about our touch solution, which has become our top-selling high-tech products and is trusted by leading global home appliance makers. During this session, I will cover the key development processes behind our touch application programs and configurations. First, we'll explore the ABOV website for materials like data sheets, manuals, application notes, driver code, and the example library code. Next, we'll examine the example code and development environment. Finally, using the Touch MCU starter kit with a shield board and example code, we'll set up the debugging environment, focusing on touch sensitivity tuning and utilizing a GUI tool for debugging. Okay, first we will introduce development environments. We will go through the documentations. So you can check the entire lineup and product list on our websites. If you select the desired IC package in the product list, you will be taken to a detailed page where you can download the data for the IC. You can also search by IC name, like A31T216. In the search bar, you can type the product name and you can check the documentations. The Touch MCU is based on 32-bit Cortex M0 on-core and supports up to 24 touch channels with a water shield and excellent noise immunity. Primarily, it's used in small kitchen appliances and control panels that have LED and LCD drivers. Our Touch MCUs integrate touch and the LED sensing on a single pin. So it is simplified designs and have an enhanced LED control. We also acquired the UL60730 Class B certification for improved reliability. I'd like to mention that you can subscribe to our website to receive the latest information on our touch solution. Also, things like data sheets and software materials are uploaded in separate sections. As you see here, we have two sections, advanced literature section and general literature section. In the general literature section on the right, you can find documents and general information on your target MCU. The content from both sections are basically the same, but in the advanced literature section, you will find the information in newer format, but you can both refer to both sections. The code driver touch library in the literature section is for CAIR and IAR development. Advanced literature supports materials on CAIR, IAR, and GCC Eclipse. The project structure and driver code differ, so please choose the section based on your needs. AUDK32 supports IAR, and Eclipse. Project files are in application folder. In the folder, you see that SDK. SDK stands for starter kit. For touch solution, use SDK for touch shield. Bare board is for other general boards. Select your IC there. The AUDK32 guide covers setup, pins, memory, and debugging. So you should read it before starting. The AUDK guide is inside the downloaded folder. The PLL setting guide document is commonly used for 32-bit MCUs. It includes detailed explanations of the PLL blocks structure, register settings, operating methods, and related circuits. By using the PLL, you can generate a maximum clock of 48 MHz. The circuit design guide explains the power, clock, ADC, reset, and boot pins, and we show how to set them up on your circuit board to avoid noise issues. You should check it when placing your parts. The IAR and KAI project setting guide shows how to set up your software compilers for your project, including creating projects, setting options, and debugging. You should see our example code and projects online or check the software manuals for your own settings. The user below the guide is for ABOV 32-bit MCUs. It explains how to make a bootloader for your applications, covering memory, programming, and project setup. You need to write and test the bootloader codes on your own. This LED driver guide shows how to use the MCU to control LEDs and how to connect them. It uses SAG and COM pins. You can connect many LEDs using fewer pins this way. In the example on the right, they first set up 8x7 LED matrix, which is 56 LEDs in total. Then they use the iSAG pins from 0 to 7, and they added 5 more T-type LEDs by connecting them to the shared icon pin number 8. If sharing pins, you must use a direct diode. See the left picture to avoid any noise interference. The touch design guide has more information on these diodes. Of course, you don't need any diode if you are not sharing the pin. The pin sharing works by time division technology between LED and touch functions. Example code in the shared board is included in the example code. The touch shared board quick guide has details on setup and code. The touch sensor design guide covers hardware and layout for touch. The sensitivity depends on its cover thickness, pad size, and capacitance. It's more sensitive if the pad size is bigger, and less sensitive if the cover is thicker. A 22 nanofarad capacitor on the cap pin is crucial for sensing. This cap is essential for sensing touch IC charging and discharging. You should select the best cap on the market that has the minimal offset in change caused by external temperature. And also, you should consider adding a 1000 ohm resistor to the pin for ESD protection. The UART sampling timing document is used for 32-bit MCUs as well. It explains things like the setup of UART, how the signals work, and the block diagram in detail. The noise immunity hardware design guide advises on reset, I2C, and ADC, those noise-sensitive ones in circuit design. It details PCB structure, layer connections, and power line layout for noise reduction. You should refer to the hardware setup guide for more information. Also consider leaving extra room for your PCB layout for future PCB modification when the noise issues cannot be solved in the future. Okay, I will continue to move on to the touch project setup with the starter kit. The A31T216 starter kit has built-in chip, MCU, connector, JTAG add-on, and UART. The header pins offer easy connections. The starter kit quick guide explains basic setup. You can find the schematics and design files on our website. The touch shader board has touch applications with a starter kit. It also has the M and T-type LED matrix touch pads. The example code shows touch and LEDs, and the hardware itself has mesh shield. So the water shield feature is also testable. The graphic user interface tool The GUI tool shows real-time touch data via UART and I2C. It is showing up to 6 touch channels, as you see in the image. It outputs raw data, baseline, and threshold. You can save data to a CSV log. You must use the GUI tool to check and tune its actual output data when debugging. All of our 32-bit MCUs come with 2 types of example code. One is device-specific examples. They are tailored for a specific IC part number. And the other is AUDK 32 examples. They are designed for the comprehensive AUDK 32 development kit, allowing you to select your target IC from within the kit. Both the AUDK 32 and touch example code bases share the same core algorithms and touch libraries. The key components, such as hardware settings, touch IP, and essential algorithms like baseline tracking, are provided in a library file format. These library files are not meant to be opened or modified. In contrast, the communication protocols are provided in open source code format, allowing you to review and customize them as needed. The shared board quick guide details the touch example code, including hardware and compiler settings for the circuit kit and shared board. You should start your touch application firmware by modifying this example. To port our touch example code into your platform or system, in other words, to modify the code structure, the touch library and key codes must be all included. After modifying the code structure, you should not forget to check the sensing data, test the sensing data whether it works normally. Okay, then I will switch to real-time tuning and debugging of our touch MCU. For basic touch testing, you should connect starter kit and shield board. And then use a cable, USB cable, to connect to your computer, and also to use the graphic user interface. You should connect the separate USB to UART board to the RX and TX pins of the shield board. The starter kit's A-Link debugger supports UART communication, but it uses the CS4 and CS5 pins. This means you cannot use the CS4 and CS5 for touch sensing when the debugger is connected. If you want to utilize all available touch channels, you can instead use PF4 and PF5 pins for UART communication. This allows you to free up CS4 and CS5 for touch sensing. Once the hardware connection is complete, you should execute the CAR project of the downloaded SDK shared example code. The Project Explorer displays all the necessary components based on your setup, including driver code, touch panel files, touch library headers. Once you download and run the example code without any modifications, the touch functionality on the shield board will be activated immediately. When building and downloading the firmware, the settings of A-Link debugging and firmware download are already applied to the project. To run the firmware automatically, simply reset the starter kit or reapply power. For logic debugging, you can also choose to run the project in debug mode. After running the firmware and a touch key is pressed, the LED matrix will show the corresponding touch key value. In the GUI Tools main tab, you can select UART, set the correct COM port for your UART board, and the baud rate to be set 115,000 and 200 bps. Once set, the power on button activates, establishing communication. And then you should press start to see output values in the data window. You can control data display in the UART data settings. In our example, to display two touch channels, in the configuration, you should set the start channel to 0 and set the num input to number 2. This defines how many channels you want to display. In the data display section, make sure to select all A data types. Then click the Get button. This will update the values in the data display window on the left. If everything updates correctly at this stage, it means the hardware connection and settings are properly configured. Okay, we will show the basic terminology. The raw data, obviously, it's the original signal measured from the touch channel. The baseline is a reference value representing the non-touch state. It is continuously updated through tracking. Differential data, this value indicates the strength of a touch. Detect threshold, when the differential data exceeds this value, a press is triggered. Release threshold means when the differential data falls below this value, a release is triggered. Key ID states displays the current state of the key, either press or release. The channel capacitance represents the capacitance of each touch channel. It's useful for checking the hardware status. So to customize the data types displayed in the GUI, you need to modify the dbg send data function parameter located in debug configuration file. This function is responsible for sending touch data via UART. You can edit the C code in this function to output other touch-related data according to your needs. The GUI tool supports displaying up to 6 graphs, giving you flexibility in choosing what data to show and where to display it. For example, to visualize the raw data of touch channel 0, you can configure one of the graph slots in the GUI to display that specific data stream. As talked earlier, our touch MCU uses two sensing frequencies. One channel has frequency A and frequency B. We are getting raw data for two frequencies per sensing, and we are also calculating two baselines. In normal conditions, the two frequencies from each channel is almost similar. So in this scenario, we can just test it with one frequency, which is frequency A. And the number of graph displays can be set from 1 to 6 in the data display settings. Let's change the number of graph displays to 3 and proceed. Let's take a look at the touch sensor data here. The first graph shows raw data decreasing upon touch due to capacitance change. The second graph displays touch sensitivity. If differential data exceed detect threshold, it's a press. If in press and differential drops below release threshold, it's a release. The third graph shows the final press or release state. Okay, Now let's retune for finger touch. First, to check the current finger touch sensitivity, touch the center of the touch pad 5 times consecutively at 1 second interval. For actual product development, our standard is to test using a metal conductive pole based on the product and touch specifications. It calculates maximum and minimum touch raw data and average change. Dragging lines on the graph shows the change amounts, also calculated after a long press. Currently for channel 0, the raw data is 10,280. If you touch it, it has an average differential data change around 670. Differentiate data equals to baseline minus raw data value. So let's adjust the sensitivity here. If the touch differential number is too small, calculation loss would increase. And it is hard to judge whether the algorithm works well. If the differential number is too big, it will unnecessarily increase the sensing time. A good initial differential value we recommend should be from 200 to 400. The sensitivity and touch settings can be done in touch sum count parameter. The parameter is to set the sensing repeat count. The final raw data is actually the cumulated sum value of sum count. Reducing touch sum count number, the raw data will become smaller, so the sensing time will become faster. To get differential data around from 200 to 400, you should adjust the touch sum count parameter. Currently, it is set to 8, and the differential data value is 600. We can reduce the sensitivity to 4 to make it faster. After changing the touch sum count parameter, the raw touch data on channel 0 decreased from approximately from 10,280 to 5,150, effectively reducing to about half of its original value. As a result, the finger touch differential data also dropped by half, now measuring around 320. This aligns with the principle that higher sensitivity corresponds to a larger differential value. So a lower differential value indicates reduced sensitivity. After adjusting the raw data variation during touch, the next step is to configure the threshold values used to determine detect and release events. The detect threshold is set using the threshold detect parameter. If the detect threshold value is too low, it may cause hovering effects, where a touch is detected even before the finger contacts the pad, or it may increase the likelihood of false triggers due to noise. If the detect threshold value is too high, it may result in missed touches, especially when the finger does not press the center of the touchpad. The recommended range is from 50 to 80% of the touch sensitivity. Based on the previously measured finger touch sensitivity value of 320, we will set the detected threshold to 60%, which is 192. The release threshold for each channel is set using the threshold release rate parameter. This parameter represents a percentage of the detect threshold. If the release threshold is too low, it may reduce the release detection rate under noise conditions. If it is too high, the system may detect a release even when the finger is still moving or not fully lifted off the pad. The recommended range is also from 50 to 80% of the touch sensitivity. Currently, the setting is at around 70%, but we will change it to 50%. This means the actual applied value will be 50% of the detect threshold, which is 96. On the graph, you can see that the detect and release threshold values have been changed to 192 and 96 respectively. By repeatedly touching, you can test whether the detect and release settings are appropriate. We'll now move on to adjusting the baseline, which as we discussed earlier, baseline is used to calculate the differential data. The baseline represents the average value of raw data sampled during the release state. The baseline gradually adapts to slow environmental changes such as temperature variations. The baseline follows the raw data slowly. As shown in the graph, the baseline is currently being updated every 500 milliseconds. And you can see that the baseline is not updated and remains fixed during the touch detect state. Okay, first, let's adjust the baseline update period in the configuration file. The timer-based sample value defines the sampling time of the baseline's raw data, which is the update period. It's currently set to 500 milliseconds. For testing, we can set it to 2000 milliseconds, which is 2 seconds. Next, we'll adjust how much of the sampled raw data is updated into the baseline. The baseline update speed is applied in 2 stages based on the value of the base trace speed track rate parameter. If the differential sensitivity is higher than the parameter, then base trace slow speed is applied. If it's lower, then base trace fast speed is applied. This approach is based on the assumption that a small differential sensitivity is more likely to be noise. So the baseline is updated faster to reduce noise. A large differential sensitivity is more likely to be an actual touch. So the baseline is updated slower to avoid losing sensitivity. The base trace speed check rate parameter is defined as a percentage of the detect threshold value. For the tests, we set base trace speed track rate to 50%. We are now adjusting the baseline change speeds here. If both values are set to the same number, the dual speed feature will be disabled. For testing, we change the fast speed value from 1 to 10. Now we'll update the device software with this new baseline configuration parameter. The baseline is still changing slowly, as you see here. Its speed affects touch responsiveness. Too slow, might miss quick taps. Too fast, might misinterpret noise as a touch. We discussed the key baseline settings. Touch sensitivity also depends on hardware. The example settings are starting points, tested in various situations. If you want to adjust, you should carefully analyze issues and test this completely. Okay, besides what you can find on our websites, we can also provide UL 60730 Class B library code, graphic user interface tool, and if you need, of course, we can provide the instructions for using touch view and slide features for our touch mobile applications.